Hi, I'm Glenn Nausley with Promess Incorporated. I wanted to talk today a little bit about the assembly of a carrier for a transmission. The carrier itself it's actually a very complex part in how it functions, but it's a pretty simple part in a lot of ways. I mean, basically, you got a carrier housing, you've got the pinions, and there's what they call pinion shafts. I always call them pins, but apparently the industry calls them shafts. And there are a couple of washers, top and bottom. And sometimes you get double carriers that have another row of pinions, but these are simpler. And when these are assembled, the machine will put the washers in and the pinions in, and then they press the pinion shaft into the housing. And there's some complication in doing this press that Promess helps with, and that's one of our major core competencies actually is putting carriers together. But today I'm not going to talk about pressing the pinion shafts. That's for another video. To keep this video simpler, I want to talk about the staking of the pinion shafts, because once they are pressed into place, the pinion shafts are staked both top and bottom. And there's kind of a cool technique Promess uses during the staking that is, I think, pretty unique and clever and interesting. So basically, I'm going to talk a little bit about the old way, the way it's been done in the past, and then the Promess technique and how to do it, and the advantages of the Promess technique. Most of the advantages of the Promess technique, it helps control the depth of the stake, which is really the critical thing that the customer is looking for. But it also helps with the monitoring of the staking depth and the staking force, so you know that the stake has been done properly. In order to accomplish this technique, we use a Promess electromechanical press. This is a standard Promess electromechanical press. This is a 3 kilonewton unit. Usually we use, I believe, a 40 or a 60 kilonewton unit to do this staking. This is like 600 pounds. It probably takes 6,000 to 9,000 pounds, maybe as much as 12,000 pounds to stake these top and bottom. We have an encoder on the motor. So with the encoder on the motor, we can measure the position of the press. We also have the load cell here, so we can measure the force. So a standard press has the load cell and encoder mixed in. I'm going to show in a little bit. One thing we've done is we've added a measuring probe to this application also. The measuring probe comes back to the same control, and we can use the measuring probe for control or just for monitoring. So talk a little bit about how this is done in the past. In the typical way to do the staking is you set this part down and it actually sets on the bottom tools. The housing isn't supported at all. These pinion shafts are pressed in, or pinion pins are pressed in. The part is set on the tooling where the bottom staking tools are holding on the pins and supporting it. And then a hydraulic press with a staking tool comes in from the top and basically pinches or crunches these two together. And it's done usually to a force. It can be done to a dead stop on the tooling, but normally they just have the hydraulic pressure set to 8,000 or 9,000 pounds, whatever it needs to be, and it comes down and presses to a force. That's the standard way of doing it. So it's basically you're pressing, you're hoping your tooling is good, you're hoping your pinion shafts are of the proper hardness, and so that if I put a certain amount of force on it, I'm going to get a certain amount of material flow and a certain amount of stake. Well, what the technique we have used in order to kind of improve that is using a Promess servo press with the tooling, same as with the hydraulics. The difference is the tooling on the bottom is the same, but you have a platform here that supports the housing, and the press, you have springs that push this part up and hold it off of the tooling. So you're not touching the tooling at this point, and we're not touching the tooling at that point. These springs are holding it up. And we put a measuring probe that measures the height of this plate or of this platform that's holding the housing. So now when the press comes in and presses to do the staking, it pushes those springs down until you make contact with this tool. And when we press this down, because we have the load cell here, we press until it makes contact with the tool, and we can feel that it made contact because the load cell off of the press, once the housing is pushed down and these come together, maybe we'll set a limit at 100 pounds or 200 pounds so we can feel when those two touch. Now we know the tooling has made contact. The goal is to get a 1/2 millimeter stake depth on top and a 1/2 on the bottom. So that means the press has to move 1 millimeter. And if everything is perfect, the pinion pin has the same hardness, so the material flows the same on top and bottom, and the tooling has a similar geometry. And if the press moves 1 millimeter, I'm going to get 1 millimeter, a 1/2 millimeter of stake on the top and a 1/2 millimeter of stake on the bottom. Now we don't take that on faith, but that's the press moves 1 millimeter after the touch point. So it comes down, finds the touch point, presses 1 millimeter, and then comes back up. Very simple application. The part spins, we hit the next one, part spins, it hits the next one, and so on. What we end up doing with the advantage of this is the total stake depth is controlled from the touch point. So we know that we've come in and we hit and we move 1 millimeter, which will be a 1/2 millimeter per top and 1/2 millimeter per bottom of stake. The top and bottom stake depths are monitored individually, and I'll explain how we do that. The top and bottom force depth signatures, so we do signature analysis, that's measured individually, and I'll explain how we do that. We can detect uneven staking, total tooling wear and failure. If your tooling top or bottom is wearing or is broken, have a chip or something, you'll get a different kind of flow, a different kind of force. You'll see that. And the pinion pin quality. Sometimes these pinion pins, because they're hardened, but the tops aren't, the top and bottom of the pin is not hardened because you need that material to flow. And sometimes if they're not hardened properly, the system will tell you that. So basically, the housing is supported on a spring-loaded platform. The tooling to stake the bottom is located below the pin. The press comes down, hits the pin, pushes it down until it captures it between the upper and lower tooling. The press can feel that it's captured because the force starts to climb. It grabs that position point and then presses a distance from there. So we're controlling that. So that's how the motion is controlled. The cool thing and interesting thing is how the monitoring is done. The raw information which is captured, we have an encoder and we have a load cell. So we have, as the press is moving down, it hits the part. When it hits, the force jumps and then it moves 1 millimeter. And so you have this curve, and that is the raw information off of the press. Now we also have the probe on the bottom of the platform, measuring where the platform's at. So we take second raw information, which is really telling me what's going on in the bottom stake. That's 100% what's going on in the bottom stake, because when it comes in, you get the touch point. So I have my probe down here and my force up here. So it's the force off the load cell, but the position off the probe. When it touches, it comes down, and whatever amount that this platform moves is the staking depth of the bottom stake. So the bottom stake is very clear what's going on. I can see the force curve. I can see, did I really go a 1/2 millimeter, or was the part too hard and this only went 1/4 millimeter and the top went 3/4 millimeter, or vice versa. So that information is really clear. But how do I know what happened on the top stroke, on the top stake? If this is my total and this is what happened on the bottom, I can subtract this curve from this curve, and it gives me very detailed information what happened on top. And that's basically this thick paper doesn't want to bend. So we get the exact same curve if we take the press information, the total information, minus the lower stake, which is the force off of that probe, that gives me my upper stake. I get a curve, which is the total curve minus the bottom curve, gives me the information for the top curve. And this is 100% isolating the information from the top. So I can say what was the depth and what did the curve look like. And with that, I can detect. Again, it really tells you everything you need to know about the quality of the stake. What was the depth of the stake? What top and bottom? What was the symmetry from top and bottom? Do I have a problem with tooling? Do I have a problem with parts? So there's a ton of information there. And this was kind of a cool application. And again, we did it the first time probably 12 years or more ago, and have done it many, many times since then, the same application. And this, on this carrier, it's kind of a good it's a good example. But anytime you're doing top or bottom stake, this is a very common thing for people to stake two sides by having a stationary tool and a moving tool. This technique works. So if you have any questions on this, if you have an application, a staking or crimping application or a press fit application, that is what Promess does. We're experts at it. We sell a whole variety of presses, from this again is a 3 kN press, around 600 pounds. We have applications that go up to 400,000 pounds with fully electric servo presses. Feel free to give us a call. We have a whole team of application engineers be happy to talk to you. It's the phone number is 810-229-9334. Our website is promessinc.com, or you can email us at sales@promessinc.com. Thank you very much.